Hello and welcome to Focus on Geothermal Energy for the Weekend webinar by Think Geoenergy and Enerchange. My name is Alexander Richter. I'm the founder of Think Geoenergy, and I'm pleased today to have this webinar on enhancing geothermal well efficiency using unconventional drilling technologies, with a great group of people here from the industry providing incredibly insights here into drilling technologies. The participants or the presenters are Armin Federico from Altitude Energy Partners, an operations engineer with a great experience in engineering and technical sales roles at various service partners in the industry. Walker Olson, an accounts representative with NOV, and a great background in geothermal drilling programs such as Utah Forge, Calpine, and Fervo. And last but not least, Rickey Bird Jr., the business developer with Sinclair Well Products and Services, with an extensive background in the oil and gas industry as well. And with that, we want to jump right in. There's a lot to cover here, and I'm handing it over to Armin Federico here to start his presentation, and he will then be followed by Walker and Rickey. After the presentations, you have the option to ask questions also during the presentations in the dashboard of the webinar. I will then try to group these questions as much as I can and then give it to the presenters so we can see how much we can manage to answer questions after the presentations as time permits. And with that, I'm handing over to Armin. Armin, over to you.
Good morning. Thank you, Alex. So this morning, we're going to discuss how our role in has been done within the geothermal space here. So we've been utilized, let me get the next slide there, utilized as a directional drilling service partner in various geothermal projects in the past couple of years. We've been using our unconventional experience in normal oil and gas and applied it to the enhanced geothermal system developments. And with that, we've shown well-to-well performance on commercial projects, major commercial projects in the US. And then also another project, we were able to prove out that EGS proof of concept in a confirmed pilot project, and this was also implemented in a large scale in Europe. So to discuss the keys to success, we go to our project planning. So with that, we've got our hot hole experience in the basins in the US, and we also utilize the Forge offset data in Utah to prep for these projects. We meet with customer, go over their requirements, any other requirements if ROP or hole quality are primarily the focus, where we begin our review, and then our project planning, to where we utilize the fit for purpose personnel, products, and service type, and then go over a risk assessment on all the hole sections that are going to be drilled. And with that, we go into the service execution, to where we drill the well, monitor real time any issues or concerns, any service interruptions, and then after completion, we go over debrief, performance evaluations, KPIs, any NPT that's incurred, and then ensuring that we're in constant communication, ensuring the satisfaction of the well, and any changes that need to be changed between wells. So with that, there could be an MOC where we change technology, or any different designs in bits or BHAs, and any issues with the high temp or high abrasive formations to make any other changes. Okay, so to allow for this performance and consistency, we ensure that there's constant communication between ourselves the operator and other service partners on the project, so that any upgrades or changes in designs are all aware between all teams, and the issues are corrected for. So the main role of all this communication is to optimize our bit and BHA life, and utilize our experience to make informed decisions from well to well, further increasing our performance. So just it's the main theme is constant communication between all the teams to make sure if there's any changes, we need to test compatibility with elastomers or ensure that we're getting proper weight to the bit, that everyone understands their roles. So all our milestones and KPIs are met. So some of the planning on our side is for the directional objectives, we want to ensure the BHA is designed correctly, whether we're going to do just a deviated well or a full-on horizontal. We'll utilize different stabilized or slick designs, or if a rotary steerable is needed, we will mobilize one as well. So all the planning is done on industry standard modeling software, and as we go and drill and utilize our KPIs from subsequent runs, we'll make adjustments as needed. So sections of large granite while we were drilling these projects required us to research and introduce high wear resistant materials and focus on other technologies to help increase our ROP and wellbore placement. So other things that we had to utilize is friction reduction tools, roller reamers, various lubricants and additives to help reduce high torque steam in these various projects that we've achieved. Some of the outputs of our modeling is we can do build-up performance, so we can predict build rates of BHA that are designed, as well as rotational tendencies in order to adjust stabilizer placements and minimize slides in laterals, or in all hole sections. So again, our various well objectives, as we drill these, we'll see the achieved wellbore placements. For example, here on previous wells, we'll plot motor yields and inclinations and ensure that our BHA designs are able to achieve those, or if they're overachieving, we can reduce the bends and allow for higher RPMs when we drill out into lateral. So, and again, after each hole section and each well, it's communication between all the groups to ensure that all the designs are compatible. So again, with the post-run analysis, after each well, we'll reiterate and redesign if needed. So again, do another BHA modeling, adjust stabilizer placements, analyze build rates, and then as well as do critical speed analysis, which will ensure that any parameters that we deploy are not within drilling dysfunction nodes. So, and again, with our experience, we've just developed, we've utilized our hot hole experience to develop procedures within it for drilling geothermal wells. So, for example, in some of our basins, in the Haynesville and South Texas, we've ordered some of those trip procedures to ensure that temperature is minimized while tripping in the hole. Also, we've utilized that experience to ensure fit-for-purpose MWD tools are utilized to minimize risk of failure or battery issues as well. So, and utilizing those fit-for-purpose MWD tools, our real-time setter and our field team are allowed to monitor for drilling dysfunction and ensure that all energy is directed to the bit. If we have multiple runs, we'll download the high-frequency data from the tools and the other sensors for analysis and adjustments to our procedures going forward. With all of the pre-planning execution, we were allowed to meet all our critical wellbore objectives. So for these couple projects here, all the communication allowed us to optimize our drilling and help our operators prove out their projects. So performance improvements we've seen have allowed them to further receive funding, proof of concept, and allowed for these projects to grow. So truly pivoting our unconventional experience to EGS, we've allowed these operators to prove their concepts, reduce overall costs, show improvement well to well, pad to pad, allowed for increased reliability within our systems as well as the rig, and then showed that EGS is scalable with high confidence and sustainability, and can be maintained. Alex, that's me. Yep, thank you.
Okay, then over to Walker.
Awesome. Yeah, really exciting stuff, Armin. It's been fun seeing you guys contribute. So, my name is Walker Olson. I'm an account representative with NOV and specifically inside the read hike log department. So PDC drill bits is kind of our niche and where we're seeing a lot of success recently. So covering today, I'll just kind of talk about some historical case studies of uses of PDC drill bits in geothermal applications and just kind of talk high level about some challenges specific to geothermal operators, some of the best practices that we learned and results in action, take a peek at some data and things like that from the USAW Forge project, and then some lessons learned and just kind of where we're at as a geothermal industry using PDC bits going forward. So Armin, you can probably go ahead and skip forward 2 slides here, but looking at the challenges first, go ahead to the next slide. So challenges that are kind of specific to geothermal operators, and really I would throw oil and gas wildcat wells in the same boat as these, but available data is really hard to come by. A lot of operators are coming to us looking to drill wells in areas that aren't typically drilled with oil and gas offsets. So lithology is a big one. It's mostly unknown. We've got a few operators, going into basement rock for EGS projects or things like that, where offset data and historical wells are limited, or even if they do exist, you're looking at BHAs and bit records and drilling programs from back in the early 90s or early 2000s, where the majority of it was drilled with PDC drill bits, with roller cone drill bits at that time. So we're looking at a lot of data trying to figure out if PDC bits can be compatible for the same well bores. High temperature bottom hole. I know that Armin and Rickey are going to talk about this some in their presentations as well, but just the heat, what that does to BHAs. I think where PDC bits can kind of fit into that is hopefully drilling a little bit faster, rate of penetration, potentially limiting the amount of time that those tools and everything are downhole. Lost fluid and air drilling, these are kind of specific out to the geysers and areas like that, but obviously that add some challenges in on the PDC drill bit side, particularly with just drilling dysfunction, high vibrations leading to shorter runs, downhole tool failures, things like that. So there's a lot of juice left for squeeze here on the table with available oil and gas technologies that can just pivot directly into geothermal already. So I think that oil and gas service companies have really risen to the challenge there of kind of providing some more bulletproof BHAs that can really drill extended footages and get to TD with the maximum amount of cost reduction. Horizontals, this has been kind of a newer development with Fervo and a couple other geothermal operators, but drilling horizontals is not new for oil and gas, but the difference for geothermal is you got the high heat, you've also got typically some more challenging rock there. So we're still working towards, for Fervo specifically, just getting to longer laterals. We're doing a lot of bit redesigns, PDC bits, trying to get over 3,000 to 4,000 feet in these laterals is where we're hoping to get in the next year or two. So a lot of things to learn there and a lot of data to become out of it. And then rapid failures, I'd say one of the main differences in geothermal is the challenging rock. So a lot of it, the reservoirs for geothermal are in granite, basalt, air drilling, things like that, where you tend to, in the oil and gas industry, see a kind of gradual procedure to bit failure or motor failure, something like that. In geothermal operations, and specifically for Utah Forge project and areas kind of around there, the bit failures were just very rapid, where we would look at MSE data and see that our bit was more or less fine, the BHA was drilling efficiently, and we would basically trash a bit and be tripping in less than 2 feet. So rapid failures there. Go ahead to the next slide, Armin. So just looking at best practices next. So these are just some lessons that we learned kind of going forward from the Utah Forge project. These are things that are not geothermal specific, but they're good for running an operations team efficiently and kind of bringing in your service providers. So everybody being on the same plan. This was something that grinded on for the Utah Forge project and for a few other of these geothermal operations, but we had daily calls every day talking about what's limiting us from going faster ROP wise, what's causing bit trips early, what can we do parameter wise, what can we do design wise with the BHAs to extend run life, things like that. So kind of just talking specifically about the parameter optimization, using MSE or mechanical specific energy has proven to really extend bit life, particularly on the Utah Forge project is where we, I think, used it the most extensively. But really every time we were breaking in a BHA, we'd do a weight on bit step test, followed by an RPM step test. And what we're modeling there or looking at is the downhole and total mechanical specific energy, and we're trying to find just the right parameters to where we're putting as much energy into the rock efficiently as we possibly can. So this also helps us avoid early bit dysfunctions and prevent cutter wear, which we'll take a look at that a little bit in the results in action page. But just figuring out kind of your operations and how you want to do it as a team, whether it's daily or weekly, kind of getting everybody on the same page is still the best lessons learned as far as what practices are leading to some of these wins. So next we'll kind of take a look at the results in action. So this first slide here is just looking at the Utah Forge project. These are not specific to the Utah Forge project. We do these for a lot of operators, but I wanted to just highlight that we do have a lot of non-disclosure agreements and things in place with some of our operators here. And so this data is readily available because it was part of that project. So I figured that we just talk about that for a little bit. But what this graph's kind of showing is just the progression of wells drilled over the years. And it's specifically looking at on bottom hours because we wanted to pull out trip time, there were some coring times, things like that during these projects, but massive gains as far as drilling efficiency from the first well that we drilled to the 5th well that we drilled. And really the reduction in time here is directly contributing to the cost of drilling those wells and the cost that it takes to put these EGS systems together. So we're very proud to participate in this, and we're excited to kind of talk about some of these results. So on the next slide, I'll kind of talk about a parameter trial that we did. So this is just one example of kind of what we talk about in those daily meetings, where we're just trying to figure out the incremental steps that we can take to make the drilling more efficient, to get the most out of our bit life, things like that. So just an overview of this Forge 16B well. There was a lot of coring and a lot of sample testing being done during this, which limited our run lengths to about 500 feet per run before we were doing cores and stuff. So it really let us look at parameter trials heavily, just due to the shortened run length. We weren't necessarily scared of making that 500 feet footage every time, whereas in some other operators, we're trying to just increase footage as much as we possibly can. But the parameter trials here and the lessons learned from this well are still being implemented with a lot of our operators today. So one of the goals of this test, and what we're kind of looking at right here on this slide, is we had 2 different BHAs, BHA 11 and BHA 13. We ran the same BHA layout for both of these, so the same bit, same motors. We were both in the tangent at the same time. And what we were kind of looking at was cutter wear, and specifically how to minimize our cutter wear, as well as increasing ROP. So on the right side, you're kind of looking at the distance that a shoulder cutter of a PDC bit would travel. So faster ROP, if you think about how far that outside cutter is traveling, it travels significantly less when you're drilling at a higher rate of penetration than when you're drilling at a lower one. So trying to minimize the cutter wear on the shoulder, pushing a little bit harder on the BHA and getting a faster rate of penetration is one of the best ways to minimize that cutter wear. So what we specifically looked at was keeping our bit rotating RPMs lower than we did on the first BHA during rotation. So we wanted to keep them right between 180 and 200 RPMs. And we wanted to also just do the same thing that we always do, which was a weight on bit step test to find out where that lowest MSE value would be and kind of run it as that. And then sliding, we wanted to increase our bit RPMs during that sliding interval, just to keep the ROP up a little higher, because back to that slinky on the right side, the slides, when you're sliding at 20 feet an hour, putting in a 20-foot slide, those bit RPMs add up really fast, and is kind of detrimental to our cutter wear. So on the next slide, just highlighting kind of what our typical cutter wear looks like. If you want to skip forward one, Armin. So the typical PDC cutter on the shoulder, what we're looking at is the thermal wear / abrasion wear that's minimizing this. And as the cutter doles off, your efficiencies will drop, the ROP values will kind of taper off, and you get kind of a maintained ROP. So going from 1 to 4 in that picture is kind of how our wear flat progresses, specifically in the Utah Forge project, where we saw just the granite kind of taking away that tip, the chamfer tip in cutter 1. And then as it continues on to cutter 3, you see that wear flat just growing. And then once you get to 4, that's kind of where the spall crawls down the face of the diamond table. And I mean, it's not hard to think of just when you're drilling on a cutter that looks like number 4, that your efficiency is going to decrease pretty extreme compared to having a sharp cutter in that place. So on the next slide, I'll just kind of show you, this is BHA 11. And what we're looking at here on the left side is just a depth versus on bottom hours plot. In the middle, you can kind of see the parameters, ROP, weight on bit, bit RPMs, and flow rate are kind of the ones I wanted to highlight on that plot, just over that 500-foot run. And then right in the middle there, the parameter medians. This is just putting time-based data into Tableau and kind of pulling out what those values were at for the median. So, you know, half the time you're going faster than that median ROP, and half the time you're going slower than that median ROP. So just looking at the flow rate, bit RPMs, and rate of penetration from that plot, you'll see that our slide percentage, which is the right of the median values, is right at 27 foot an hour. And that's with lower bit RPMs than what we had when we were rotating, and lower flow rate than what we had when we were rotating. And overall, I mean, this run, we were so-so about it, you know, 500 feet at 80 foot an hour in granite. There was a time where we didn't think that this was going to be possible to drill granite with PDC bits, but we felt like there was more juice on the table to squeeze. So we kind of brought to that all-in hands meeting the fact that we wanted to try tweaking parameters and looking at ways that we could increase that slide percentage as well as decrease the amount of wear that we were seeing on the bit. So once again, just 500 foot run, 80 foot an hour, just keep that in your head for this BHA. And then looking at the next slide, so this was looking at kind of the results of what we tried out. So you'll notice that the bit RPMs basically stayed right at 200. I was thrilled about this. You know, sometimes we pitch ideas to operators of how we think we can do it, and then the execution isn't quite there, but the Utah Forge team was right on line with what we were trying to do here. So we kept the flow rate a little bit lower during rotation than we did in sliding, but you'll notice that the sliding ROP, which is the right value of that median parameters plot, jumped up to 57 or 54 foot an hour. So we got almost 100% increase through this parameter trial for our sliding ROP, which was awesome. And then on the far right, kind of just what that overall produced, you know, on the first run, we had 500 feet at 80 foot an hour. It was a so-so run. We were all right with that, but we felt there we could go better. So we had a 545 foot run at 109 foot an hour, which, you know, small gains, but this is kind of a just snapshot of what we're looking at in each run and for each BHA of how to improve those lessons learned and really kind of add value as we drill through these well progressions. So looking at the next slide, this is kind of a comparison of the doles here. So on the left, we've got the first parameter trial from BHA 11, and then on the right from BHA 13. So you'll see just on the left, those spalls kind of crawl down the shoulder. The wear flat that you see on the cutter is a little more you know, sporadic, things like that. On the right, it was definitely better. You know, we had less of the spalls that were crawling down the shoulder. The cutters were a little bit more in shape that they're designed to do. And just from small incremental gains like this, kind of added up over the whole span of that program is kind of how we went from well 1 to well 5 of really increasing those performance gaps. So on the next slide here, this is just something that is specific to geothermal, but is also implemented for a lot of our oil and gas operators. But just correlating our modeling is kind of shown here on that cutter tip temperature that's on the bottom left plot. So you can kind of see those 5 or 6 cutters that are right in the middle that have the yellow star over them. Those are kind of the highest modeling temperatures from what we're getting out of our modeling software. And then on the right side, you just see the correlation there to which cutters are being damaged more than others. So we're seeing a lot of correlation between our cutter tip modeling and what the doles are looking like in the real world environments, which is a great thing that we can model that stuff and kind of take that into account. So what we're doing here, if you want to skip to the next slide, Armin, is when we model these bits specifically for geothermal, but we also do this a lot for our oil and gas operators. But on the top here, you're seeing a heating for the cutter tip temperature. And on the bottom, we're modeling our fluid hydraulics for that same bit. And we're trying to get as much of a correlation of our fluid modeling to that cutter temperature as we possibly can, just to make sure that we're getting fluid to the cutters that need it the most. And by doing that, we've helped, prevent dulls, prevent early bit trips, and prevent that spall from really cutting runs short. So skipping forward to just overall the lessons learned. So this is a pretty dense and heavy slide, summarizing just the Utah Forage project specifically, but we also have seen, incremental gains like this in a lot of other geothermal applications. But the first well at the top to the last well drilled at the bottom. So, I mean, there was a time looking at the 16A, the first well, where we weren't really sure if, you could drill granite with a PDC bit. So there was a lot of lessons learned on that first well of just figuring out that we can still use the mechanics behind a PDC drill bit, shearing that granite and really grinding the well, and that our cutters that have been developed over the last 20 or 30 years, the incremental gains from those cutters is able to withstand that. And then moving down, we ran some higher diamond volume bits, so like some 8 blades, 13 millimeter cutters, things like that. And then the third well, we were figuring out that we could really push on parameters, really run an MSE study to figure out exactly what our bit was like downhole. And then the fourth well was the last one drilled. Those were the shorter runs, so we did a lot more parameter studies, but really just looking at how we can prolong bit life and stand up to some of these challenging applications. But overall, I would just say that, man, it's been awesome to be a part of this ride, and our team's been doing a great job as far as bit modeling and providing that kind of service to customers while we're out there participating in these projects. So with that, I'll hand it over to Rickey Bird, and we can talk a little bit about Sinclair's participation.
Awesome. Thank you, Walker. And thank you, Jennifer and Armin, for bringing me on board with this. I'm going to be talking about a test we did on lubricant in the geothermal space. We did a paper for the GRC, and this is going to be basically the information we kind of came up with. We had Brittany Gerke, myself, Ron Tate, John Tuttle, and Trey from ChemJet on this. So you can go to the next slide, Armin. So basically the abstract, and we're trying this sometimes, in conventional geothermal, we're not using lube per se, but in the EGS, it was very beneficial. There's a lot of challenges: torque, high abrasion, casing and drill pipe wear, and then just increased drag and weight when they're coming in and out of the hole. Next slide. So a lot of this is blended from what we've learned from oil and gas, and at Sinclair we're very diverse in our fluid. We work with foundation, environmental drilling, water well drilling, oil and gas, and geothermal. And the cool thing about that is we're able to put all those technologies together and kind of see what would benefit us in this next space. And I think with this lubricant issue, lube is, like I said, not used a lot in geothermal and conventional. So bringing that kind of oil and gas side of it into this geothermal, I think was a huge benefit. Next slide. So and I kind of touched on this too, and I know these slides have a lot of info on them, but basically, we were having some issues with excessive torque and drag, especially when getting into the granite. We needed the lubricity, and without going straight to an oil-based system, we wanted to stay in more of an eco-friendly water-based drilling fluid. The best way around that is getting this lube. Now, when we were doing the lube, we were having issues because also with high temp, you have issues with corrosion, things like that, where things break down, and a lot of these drilling fluid chemicals will break down. what we did was we tried to find the happy medium with pH, because with lube, sometimes you have what's called greasing. And, you know, if the pH is too high, that will cause that. So we were trying to find a happy medium where we could still prevent corrosion to the drill string and the, you know, tools down hole, with still providing that lubricity. Next slide. So we did some pre-qualifications just to narrow down to 3 lubes, and these are our 3 lubes, lube A, lube B, and lube C. We were trying to find greener projects for the geothermal, you know, without hydrocarbons or, you know, petroleum-based hydrocarbons. So we tested things through, we tested all these lube samples through a hot roller oven for about 24 hours and some a little bit longer, just to see what the stability would be like for these lubes, because there are a lot of lubes on the market. However, you know, we have issues with pH and heat, which, you know, kind of, you know, slims that list down a little bit. So we did some ambient low temp testing, basically like friction tests, metal to metal type stuff, and then also included that data with the hot roller oven to kind of see where we were at with these lubricants. Next slide. So here you see a chart basically on our lubricants. You know, the pH is a little bit lower, kind of like a you know, low pH. Then we bumped up some of the higher pH to figure out, you know, what would happen with that heat and with that higher pH. And that's where we kind of found out that, you know, about 9.5, no more than a 10 pH would keep us from greasing out the fluid. We did see torque reduction, as you can see on the side. The torque reduction, I mean, is huge, especially, you know, like, you know, when we're talking with Walker and NOV, you know, keeping those bits intact, preventing bit runs, things like that, you know, coating the drill string, and then just getting that higher ROP. So the torque reduction was huge, but lubricant 3 really wasn't showing that great of results. Next slide. So this is kind of what we stimulated with ChemJet, and we had some samples from the Forge project and also samples, I think, from Fervo. This is kind of an image of showing that basically, you know, there's a bit that stimulates and you can kind of see a ring within that. That's, oh yeah, this is from Forge. But basically the drill, it's like a drill simulated bit goes on top of that granite sample, and then they see what kind of torque reduction will happen, and it's a very cool thing at ChemJet. Next slide. So we prepared all these samples at just 2%. We saw that, you know, 3 or higher, 3 would probably be the max, but over 3, it was, you know, we weren't seeing any different results. So we just kind of stayed at the 2% for our testing. Next slide. So this is a picture of the simulator at ChemJet. If you look up there, you can see the little bit device that would go into the granite. It was basically, it simulates, you know, drilling through the granite and then what the torque reduction would be. So we did apply different types of torque to, or different force to record the torque. We did 150 pounds, 200 pounds, 300 pounds of force, and then just kept that same percent of lubricity in the sample. We were also able to change the temp, which was really cool about this device. So we were able to do the higher temp on this, which was pretty cool. Next slide. So this shows just the results of our test. The co-friction, the first one would be just water, so that's why it's going to be so high. And then you can see the lube 1 is really doing really well through that. Lube 2 still really good, and then we did have a couple other lubes just to kind of see what was going on, but really the lubes 1, 2, and 3 were what we were focusing on. The red lube was probably the worst one, but again, yeah, this is what makes this test interesting. Is you see the pounds going up. They, you know, the first and third lube are really staying tight and keeping that coefficient down. Next slide. So we did another round of tests. We bumped up a little bit more of the percentage just to see what the impact would be. And these are the results. Next slide. So these are still, we're still seeing the lower rate on lube 1, or, you know, the first lube A, and this is where we knocked out the other lubes. But this is where we've also upped the temperature, and you can kind of see lube number 1 is still staying pretty good with lubricity, doing great right there. Next slide. So, and this is kind of rehashing out what I just talked about, but I think basically what we're doing here is we're trying to, you know, emulate what it was going on downhole to see what the best lubricant would be. And this is where we kind of did the base pH at 9, because that was a kind of our sweet spot out in the field. And we were running these tests in the lab and also at Fervo's location on some of their wells. And we did some of this stuff with the items and granite samples from Forge. Next slide. So this is where we were doing our field tests with Fervo. We basically implemented field testing based on laboratory results. We were working with the drilling team. We added the lubricant to active drilling fluid systems in multiple wells using various methods. One of the things we observed was the improvement, and there wasn't a lot of more improvement past 3% added to the system, but it did improve the torque, drag, ROP, and many other issues that we were having. We monitored the drilling fluids and the impact of the lubricant on the fluids and properties and all that. And we just adjusted. And like I said before, we were getting some greasing at a higher pH. So we adjusted that pH, and then we just kind of found the sweet spot for that lubricant in the system. And, you know, it was really good. Also, spotting that lubricant before we ran casing was a huge benefit as well. You know, it kind of just gives you the lubricity needed to get that stuff through those horizontal areas or any type of angle. Next slide. So we can see kind of the reduction in the hook load with the lubricant. As you see here, you can kind of see that it's falling off, and these are multiple wells, or actually, I'm sorry, this is multiple trips in one well. So we kind of see the hook load dropping off here. Next slide. So I think we had a bunch of positive results here, and I think with you know, the future of implementing this lubricity treatment is going to be huge, because again, we're keeping the drill string, the drilling, you know, the drill bit, all the BHA downhole, we're keeping that all lubricated, and I think we're extending the life on that. They did mention that soaking, they saw some difference from soaking, because remember at Forge, at Fervo, we're drilling through a lot of granite. So they're saying that soaking time was, we were seeing a difference with soaking time. And basically what that is when they're letting the lubricant soak in the hole. I feel like, you know, once it's in the fluid, you're going to see results anyway, but soak times versus just doing sweeps of lubricant, we were seeing better results. Next slide. So basically the conclusion, and sorry, this slide's kind of a mess and a lot of stuff on here, but we're constantly doing research and development to enhance ROP, shave off those days on the drilling, and then, you know, just keeping that hole stable and getting that ROP that's needed. The results from the testing implemented has identified a hardy lubricant for geothermal industries. Results include consistent reduction of drilling torque by 16% after coating time and a reduction of 0.6 rotating friction factor to 4.5 friction factor and a reduction of 170 pounds of hook load during the casing running. So they've also achieved a higher weight on bit due to decreased torque as we drilled to the end of our horizontal wells compared to wells without lubricant. So this is kind of where we, you know, didn't have lubricant before, had lubricant, and saw really good results. So basically our goal is to continue this R&D to see if there's other things that we can do to help our customers in these projects get to their pay zone faster and cheaply and cost effective. And we're going to continue to keep looking at different lubricants within our lab and keep finding the best possible solution for geothermal and the EGS market. So that's all I got. Thanks so much for having me.
Wow, wow! Thank you so much. Very detailed presentations from all of you, and really good insights. Again, to the audience, we have 13 minutes left in time. If you have any questions, there are a few here. So just put the questions into the question panel of the webinar. But I have maybe some general questions, and I'm not sure who of you will answer. But the first question I have is basically for someone that is not involved in, let's say, drilling decisions here in the use of technologies and testing technologies. Who's ultimately the key decision maker for, let's say, some of this decisions on testing new things in projects? I assume that, of course, a Utah Forge project and a private sector development is slightly different. But who are the key people that kind of sell internally or make the ultimate decisions for these new technologies? Would any one of you have a point here?
Yeah, I can take that. I think that typically, so on the drill bit side of things, we work with a variety of engineers as well as rig site personnel, and I wouldn't say that it's one size fits all as far as which person's making that decision. I think on the service side, it's our job to present the solutions and kind of things that we are seeing as clearly and as concisely as we can to all decision makers, and then whether or not that goes through into daily operations is kind of still up for debate. But in most cases, I would say drilling engineers that I've worked with, as well as rig superintendents or company men, are all in the decision-making process, and as well as the directional team. So just making sure that the solutions that we're bringing to the table kind of fit into what the entire team is trying to accomplish with each run.
Okay, then another more general question, in a sense. The slides that you showed, I think from Utah Forge, it was on the drill bits, and I think that was also communicated by Fervo, is the learnings and the faster drilling time, and thereby the saving on costs. But how relevant or how realistic is, let's say, that we can decrease the drilling cost for geothermal projects across the board, or is this limited to, let's say, one geological setting and one project, and you would still, with every well that you drill, you would start from scratch at other projects? So kind of that's, I hope I get through kind of what I want to say, but essentially it's kind of like how faster can you drill than the learnings from each project, or how much depends on drilling more on one location and then becoming faster and cheaper?
Yeah, I think there's definitely lessons to be learned from specific applications, regardless of where they're located geography-wise. I think you can learn a lot just from, you know, lithology in one place translating to lithology in another. But as far as the speed of adoption to new technologies and seeing those return, I think that's very operator specific, as well as probably a timeline on just how long their program lasts, how many wells they're going to drill, things like that. Because there's only so many things you can test for each BHA to really feel like you learned that lesson and implemented it going forward. But I see Armin, it looks like you might have some thoughts too.
Yeah, no, I just wanted to echo Walker there, but you know, running a couple of these projects in different parts of the U.S., there is some consistency with the lithology, I guess, with what we've seen in modeling of these BHAs and drilling in the granites here. It's more homogeneous than, you know, what we're drilling in West Texas, South Texas, East Texas, everywhere in the normal unconventional basins. So we've been able to use some of the learnings between other various geothermal projects to optimize as we've been going forward. So, yep, thanks, Alex.
Okay, then I jump into a few more technical questions, and of course I'm not that familiar with some of the terminology, so please accept that I might not be completely getting this right. But here a question: how accurately can you predict the BHA resonating frequency, or do you take real-time data from the MWD?
Prior to drilling, yeah, we'll do the modeling, and then we'll utilize that as our, so to speak, goalpost to stay within. And once we begin drilling and get actual surveys and progress in the well, the guys in the field will monitor real time, and if there's any adjustments that need to be made, we'll you know, change RPMs, wait on bid, depending on the drilling dysfunction scene. So.
Okay, next, like I just jumped quite quickly through this here. Do you use DOC on the bit face? Is another question.
Yes, for majority of them, usually we put that feature in for lithologies and areas where we think that we're going to have some intervetted transitional drilling, just to help limit the DOC is depth of cut for those of you who might not be familiar, but it basically just keeps your bit from overbiting and prevents torque damage in the cone. So I mean, it's area specific and it's application specific, but we have utilized depth of cut features for geothermal. Yes.
Okay, then next question: what is the typical UCS of the granite at the Forge project?
Yeah, so we're estimating it to be somewhere in the 35 to 40 kpsi range, and basing that off of some of the coring logs that we took, as well as some of the MSE values that we were getting when we think we were at our lowest maximum efficiency.
Okay, then here another question. I'm just reading as it's written here. The project is testing just technologies, or is looking as well for procedure adjustments that help improve drilling time in this HT applications.
Yeah, I think it's a combination of both. Yeah. So, you know, all of us here have been adding new technologies, and then with how that's affecting the drilling procedures, as far as, you know, beginning of runs, braking in motors, circulation, all that has been adjusted as well. So they kind of go hand in hand.
And then here a question, I guess we could spin this and also further, but here with the tighter economics of most geothermal projects relative to their oil and gas project, is funding R&D and drilling technologies for enhanced geothermal a challenge, or does it correlate with the oil and gas kind of R&D, so it allows to kind of use these synergies?
I would say it's a combination of both. There's certainly R&D that needs to still be done for high temperature applications specifically, but I also think your two methods of going about this is you either bulletproof your BHA, making everything you send downhole able to withstand that kind of environment, or the other option is that you try to bulletproof your well by running fluid chillers, things like that, something to just control the bottom hole temperature. So I mean, I think there's research and development tackling that first bucket, we'll call it, where they're trying to make motors, MWDs, anything you put down the hole able to withstand that higher temperature threshold. And then on the other side, you know, there's not as much R&D probably needed, because I think the technology is pretty readily available for cooling your downhole. So they're kind of doing both at the same time, and I think that the government investing in things like that is definitely speeding up the process. So
yeah, and I think that, like, even with jobs like Fervo, where you have a blend of oil and gas people that have oil and gas experience, and then geothermal drillers, and having those two people combined, I think that R&D that was done on both sides is helping both industries really, because we see that a lot on the fluid side, where, you know, we're like, hey, this may or may not work. We've tried it over here. We know that it worked for this field or this area, and I think that communication between the two industries is huge in the R&D.
I mean, but in this context, I mean, if you take now, I mean, you mentioned Forge and Fervo here. The Forge project, of course, is by definition an R&D project. So of course there are, let's say, there's more willingness to test things. And of course, Fervo is, under my understanding, let's say a more ready commercial project with, of course, some R&D, but maybe not as far reaching. But how do you see the importance of the continued kind of, like, let's say, R&D focused projects or Fervo in the context of developing these technologies further for other developers beyond, let's say, the Fervo Utah project or the Forge project in itself?
Well, I think Forge really, you know, they were able to test a lot. They were able to do things that, you know, when you're trying to make a profit, you know, like a commercial entity wouldn't be able to do. So Forge was able to really extend that. But I also think, you know, a lot of that EGS technology that they're learning, you know, is you know, there's not a lot of granite everywhere where you can drill. So I think, you know, there still needs to be that continued R&D, and I think Fervo definitely bringing in the oil and gas people and, you know, mixing them with geothermal, I think was a perfect blend to kind of, you know, kind of jump off of the research that Forge was doing, because, you know, Forge had a lot of like really important data, but they weren't, you know, trying to trim off days for drilling time or any of those things. And I think once you get into that commercial accountability, you know, you've got to make these wells fast and efficient, you know, for everybody involved.
So in the context of, I mean, and I guess we're coming now to the end of the webinar, and there are no further questions here. But in the context, let's say, of your oil and gas experience in geothermal, I mean, these are exciting things for us in the geothermal world to see things evolving. How much of that learning that you do now in this EGS context for Forge and Fervo would also be applicable in other geologies, geographics with different geology, for example, in sedimentary basins? Are there, let's say, options to take those learnings from the EGS settings and projects into those geothermal projects as well? Or how do you see that interconnection?
I mean, I think there is definitely, but I mean, even just like, because we do a lot of work with Calpine up in Northern California, and that's conventional geothermal. So, you know, I think with the EGS, as this, you know, grows, I think that there is a lot of potential, but a lot of times for us, it's just the high temp issues and the, you know, temperature issues and corrosion issues. And that's where we try to, you know, our baseline to then, you know, figure out what we need to do from there to keep the corrosion down, to keep, you know, the ROP up and things like that. But I think that Fervo and Forge and these projects that are, you know, pretty open with their data, well, Forge was pretty open with their data, I think is super helpful, and it helps us. I don't know about with Armin and Walker, how it affects you guys, but, you know, for the fluid standpoint, I think that we, you know, we definitely learned some really good technologies, and we were able to use that and bring that knowledge to the next project.
Yeah. Again, with Fervo and the other projects that we've done, with this high abrasion and fluids, we've been able to adjust things on some of our other conventional oil and gas areas where we're applying some of these abrasive resistant additives or hard facing onto our motors, and using some of the different modeling to help our other basins. So.
Okay, I think if there are no further points or questions, well, thank you very much, Rickey, Armin, and Walker, and of course Jennifer, who organized and put this all together. Thank you very much. Super interesting learnings here from you. Thanks for sharing. Yeah, with that, I wish you all a great weekend and hope to see you at one of our next webinars. And with that, thank you and goodbye.
Thanks, Alex.
Thanks, Alex.